Okay. All right. Yeah, great. So thanks a lot for the invitation. Uh, I wish I could join you in person. But given the distance, I guess we'll have to live in the Zoom world. Um, Please feel free to interrupt me and ask questions about anything during the talk. I don't know if I'll necessarily be able to see hands, so yeah, feel free to just to speak up if you have some questions. Okay, so I'm going to talk about a couple of things under this topic of physics beyond the standard model. um, in the cosmic microwave background. Some of this is work in progress, in particular the work I'll talk about that's ongoing with the Atacama Cosmology Telescope team, although that will be out quite soon. And then some of it is work that was recently published with this group of folks here. Um, I'll just highlight a couple of junior people, Sam Goldstein and Kristen Sorrell, who are students at Columbia with me that have been working on these analyses, and Fiona McCarthy, who was postdoc right now at Cambridge. Okay, so let me just start with a quick introduction. Although I think many of you think about the CMB regularly already. So here's a map of the cosmic microwave background and isotropy from Planck, the temperature and isotropy. There's tens of millions of pixels in this map, about 50 million pixels actually. But all of that beautiful data is fully described by a six parameter standard model of cosmology, which I hope all of you know. So what does that model tell us? What have we learned from these data? We've obtained very precise constraints on important things like the amount of matter in the universe, the amount of baryonic matter, normal atomic matter like we're made out of, the age of the universe, and also its spatial curvature, which we know is now close to flat. And we've also learned important things about the properties of the initial fluctuations that gave rise to all the structure in the universe. So importantly, we've learned that they're nearly scale invariant, but not exactly scale invariant. They're consistent with being drawn from a Gaussian distribution. They're adiabatic, where by adiabatic here we mean that all the different components of the energy density fluctuated in the same way. So where I have an overdensity in matter, I also have an overdensity in radiation, and so on. And then lastly, we've learned that there are correlations that were super horizon at the time of last scattering, which sets very important constraints on the dynamical process that could have generated the fluctuations. Okay, so given this dramatic progress, one might wonder what should we be looking at next? Well, of course, we all want to know more about the details of the physics that seeded the initial fluctuations. Inflation, of course, has beautiful properties that are very consistent with these observations, but we'd like to know the microphysics of inflation. There are broad questions about what the constituents of the dark sector are, both the dark matter, the dark energy, as well as other types of dark particles like neutrinos. So, what are their physics? Um, Related to this, one naturally would ask, are there other light particles beyond the standard model neutrinos, for which we could see evidence in cosmology, but we might not know anything about them in the laboratory if they're very weakly coupled? And maybe a broader question that follows from the second one is, are there ways that we can use the CMB as a particle physics detector to look for beyond standard model, BSM, physics signatures that so far have escaped detection? So I'll try to address some things related to all these topics, I guess, today. Okay, so the talk kind of breaks down naturally into a few chunks. I'm going to first start by talking about the primary CMB, so the fluctuations at redshift 1100, and the BSM physics, some of the BSM physics that we're looking for there. And then I'll turn to some new work, new ideas, really, looking at signatures of beyond standard model physics in the secondary CMB, so processes that happen to CMB photons as they propagate through the universe. Okay, good. So let me start with the primary CMB. Pretty much everything I'm going to be talking about here is work that's ongoing with the ACT collaboration, and I'll introduce you more to the ACT experiment in just a few slides. Good. So what does the landscape, from a high level look like? So the main quantity that we're interested in, when we think about new physics in the primary CMB is the angular power spectrum, which has been the main statistic of interest now for many years in the CMB. So we're looking at the variance of the temperature or polarization fluctuations in the CMB map as a function of angular scale. That's what this plot shows. So this is in terms of the multipole L. So large scales are on the left in this plot, and small scales are on the right. Um, the orange points on the plot here are the actual Planck data points. There's also some B mode measurements from the bicep experiment down here in green, um, which are just consistent with lensing B modes so far. And then I have some forecast data points from ongoing and upcoming experiments, and I'll just highlight the blue points, which are a combination of data from ACT, um, forecast data, I should say, and then also Simon's observatory data. And I'll come back to Simon's observatory at the end of the talk. So Planck, of course, is a beautiful experiment for measuring the temperature anisotropies. I showed you the map a few slides ago. In particular, it's basically a ideal experiment for measuring CMB temperature anisotropies up to angular scales of order 5 arc minutes or so, which is L of 2000. And what we're doing from the ground with experiments like ACT and SO is to extend these measurements out into much smaller angular scales, and then also to dramatically improve upon the polarization measurements. So the E mode polarization, which is the curl-free piece of the polarization vector field, is the main signal of interest for most of what I'm going to talk about. We are, of course, hoping to also look for the B mode signal, the divergence-free piece. But I'm not going to talk too much about primordial gravitational waves in this particular talk. So what we're really trying to do with the ground-based CMB data that I'll talk about is to push the temperature measurements out into the damping tail small scales, and then also to measure the polarization much better than Planck on basically all scales. And I'll show you some more quantitative assessments of that in a minute. Okay, so let me just highlight a few science cases to motivate why we should go out and try to measure these power spectra at higher precision. So a case that has attracted a lot of interest in the context of ongoing experiments and upcoming experiments is looking for so-called dark radiation in the CMB. So the CMB power spectra have this nice property that they are affected by the presence of any light particles, whereby light we mean masses that are less than the temperature at last scattering, so about electron volt. They're sensitive to any such light particles that were ever in thermal contact with the primordial plasma. So of course, this includes the standard model neutrinos, which were in thermal contact until roughly 1 second after the Big Bang. But there could be other new light particles that were once in thermal equilibrium with the plasma at very high temperatures, which then decoupled like the neutrinos did, and which we don't know about in the laboratory because they're very weakly coupled. So it's exciting to try to look for these. This is usually captured by a simple parameter called N effective, the effective number of light relativistic species. It's just defined as a ratio of the dark radiation or neutrino energy density to the photon energy density with some prefactors that are derived for the case of neutrinos. The canonical value in the standard model is N effective equals 3.044. It differs slightly from 3 just because of the fact that the neutrinos don't decouple instantaneously, and electron-positron annihilation is also happening around the same time. But the number 3 here is just corresponding to the 3 species of standard model neutrinos that we're all familiar with. In terms of what does this do in the CMB, the main effects are that if you increase the amount of dark radiation, then you'll damp the high L power more dramatically. You suppress the power at high L, and then you also subtly change the phases of the acoustic peaks as well in both temperature and polarization. So it's these signatures that we're looking for in the data. So here are some numbers to keep in mind. So Planck, of course, looked for this. The bound right now from Planck on this parameter N effective is around 0.2. So it's below 10% precision constraint, and it's consistent with 3. I'll tell you in a moment about the ongoing analysis we're doing with ACT. The numbers in blue here are forecasts, not real data. So we're looking to shrink the error bar from Planck by almost a factor of 2 with the ongoing ACT analysis that we're doing right now. This should be out this year. And then with the instruments that we're now fielding in northern Chile, Simon's Observatory, and then its successor, Advanced SO, We hope to continue shrinking this, eventually culminating in roughly a 1% measurement of N effective with CMBS4 in the next decade. So there's a lot of reasons to be excited and to hope that we might see evidence of new physics with these measurements. So just to give you a taste of some of the things we'd be sensitive to, with the Simons Observatory precision on this parameter, we could detect any spin 3/2 particle that was ever in thermal contact with the primordial plasma, the whole way back to the end of inflation. So if you want the time, that's some minuscule fraction of a second after the Big Bang, which is much, much earlier than you probe, for example, with the Large Hadron Collider. Um, CMBS4 pushes this then back for spin 1 particles. To get to spin 1/2 or spin 0, you need an experiment that's even more sensitive than CMBS4. But in principle, this could also happen in the coming decades. And if we made such a detection, this would be, the first time we have a direct cosmic signal from the era that's before neutrino decoupling or Big Bang nucleosynthesis, et cetera. So, within the first fraction of 1 second, which would, of course, be very exciting. Okay, so that's one reason we want to measure the CMB power spectrum at higher precision. Another reason to perhaps be interested in doing this is that there are hints in some other cosmological data sets that there could be some new physics lurking in the cosmos that we haven't yet uncovered. So I'm sure many of you have heard about the Hubble tension. This is a tension between the expansion rate of the universe inferred from, I would say, indirect cosmological data like the CMB, and the local distance ladder as measured with classical Cepheids and supernovae. So this is a compilation graph just showing a few different values. So the top ones up here are inferences from, for example, the primary CMB from different data sets, assuming the lambda CDM cosmological model. For these, you get values of around, say, 67 kilometers per second per megaparsec. And then the points down here are just two of the local distance ladder measurements. The one that's famously discrepant is the Shoes collaboration measurement from Rees et al. This measurement from the CCHP program is not really discrepant. It sort of lies in the middle. Um, but the discrepancy between Shoes and the CMB, for example, is at the 5 sigma level. We'll continue to shrink the error bars in the context of lambda CDM, but of course, the exciting prospect here is that perhaps there's some new physics beyond lambda CDM that we need to introduce into the cosmological model, which would shift the values that you infer from cosmological data to be higher. And there's been a huge amount of activity on this front, and I'll just sort of give you a taste of some of it in this talk. Um, Let me highlight a couple of important things just at the level of these data here, though. So first, it's clear that this is not a CMB systematic effect of some kind, because you could do Planck, or you could look at our previous ACT data plus WMAP. These are completely independent data sets, and you get consistent results. You could also throw away the CMB completely and just look at baryon acoustic oscillation data combined with BVN data and lensing data, and that gives you the same result. This is all coming from basically the sound horizon as a standard ruler. So it's clear that it's not an issue that's a systematic effect in the cosmological data. Whether there could be a systematic in the local distance ladder, I think, is still something people are investigating, and it is an area of major activity. But for the purposes of this talk, what we should think about is there some kind of new physics we could introduce in the early universe that would lead to a higher value of H naught from the CMB and large-scale structure data? So there's been a huge amount of activity to try to come up with such models. I'll just give you a taste of a few of these. I think there's really just sort of four classes of models that could perhaps work to do this. The first class involves introducing some new form of energy density prior to recombination. So the most famous such model is called early dark energy, where you have some new field that briefly accelerates the expansion before recombination. I'll talk about that in a little more detail in just a second. Another option is that you could modify the dynamics of recombination itself. Generically, what you want to try to do is to accelerate the process of recombination so that it completes at an earlier redshift. Some ways to do that are to introduce primordial magnetic fields or to change fundamental constants like the electron mass. And then the other options connect in some ways to what I was talking about a moment ago with N effective. So the other options involve introducing some new forms of dark radiation into the early universe, but it's known that the simple N effective, just free streaming dark radiation is too heavily constrained to change H naught by very much. So you have to actually go beyond this and introduce some non-trivial dynamics into this new dark radiation sector. And there have been some clever papers trying to build models that do this with some success, but nothing fully working. Um, the last option that's received some attention that has some phenomenological success is to introduce strong interactions between the standard model neutrino species. So when you do this, it delays the epoch of neutrino free streaming to be much later. In fact, you can delay it to be as late as just before recombination. Um, and that changes the phase shifts associated with the neutrinos in the CMB, and it turns out to yield a higher value of H naught. You might imagine, though, that this is constrained by laboratory measurements of neutrinos, and indeed that's true. But there's a small corner of parameter space that is still somewhat viable for this. So I'll just highlight that, none of these kinds of models were in the conversation when our current CMB experiments were built. Planck ACT, South Pole Telescope. Um, but these experiments have, of course, been absolutely crucial in looking for evidence of these models and seeing what's going on. And certainly, hopefully, there'll be even more clever models that we can look for with things like the Simons Observatory. Okay, so let me turn to ACT for a bit, and then give you a picture of where we're at in constraining some of these new physics in the CMB. Um, so ACT is located in northern Chile. I've actually never been to the site, but I hope to make it there sometime in the coming years. This is what the site looked like in 2021. There's a few other CMB experiments that are also at the same place on Cerro Toco. Nowadays, actually, ACT has been taken away, and the Simons Observatory has filled out much of this area over here with new instrumentation. Um, Later on, the plan is to build CMBS4 also at this same site in the Atacama. So with ACT, we observed from roughly 2007 to 2022, and we've been engaged in the analysis of the data from the last 5 or 6 years of the survey since 2021, 2022. And I'll give you a status update about that. One great thing about being in Chile is that you can cover large fractions of the sky, which cannot be done from the South Pole for obvious reasons. So the footprint that we observed with ACT is shown in red here, and it overlaps very nicely with lots of large-scale structure surveys. So we're doing lots of interesting cross-correlation science with those, although I'm not going to talk about that today. I'll give you a little more detail about the sensitivity of ACT in just a second, but I'll just highlight we've observed at 5 different frequencies. The main workhorse frequency channels are these ones at 90, 150, and 220 gigahertz. And I'll highlight that we've reached sensitivities now, so noise levels that are significantly better than those of Planck on roughly half of the sky. So we're in the process of analyzing these data in what's called data release 6. It's much, much more powerful than our previous cosmology data release, DR4, and it should be out pretty soon, 2025 for sure. So here's a taste of what some of the data look like. This is just a small slice of some of the maps. So the top image up here is the temperature anisotropy. This is like the one I showed you earlier from Planck, but now we've zoomed way into a smaller region of sky. This is the E mode polarization, B mode polarization, and then this is a map of SD clusters. This is a particularly deep slice of the data. So the noise levels, for those who are familiar, this is quite good noise levels, approaching like a Simons Observatory type noise level. One thing that's beautiful here, though, is that you can see by eye the E mode fluctuations. So if I showed you an E mode map from Planck, it would just look like noise. You wouldn't be able to see any structure in that map, but you can see by eye here the pattern of hot and cold spots that are the actual CMB E modes. So this is, I would argue, the highest signal to noise E mode map that's been created yet to date. And the full survey footprint is about 250 times larger than this little slice that I'm showing you here. So it's a immensely powerful data set for constraining cosmology. if you want a little more quantitative detail about, how do we compare it to Planck and how are we, extending into new domains, I have a couple plots that I like, which bear with me, I'll explain what's going on here. So this is again showing as a function of L multipole. So large scales on the left, small scales on the right. This is the signal to noise on the measurement of the power spectrum at that multipole. So Planck has, high signal to noise in the temperature power spectrum up to roughly L of say 2000, 1500 maybe. Um, Whereas what we pick up on with the ground-based data is to extend the temperature power spectrum measurements out to much smaller scales, as I was telling you before. So with ACT, this ongoing DR6 analysis, we can take the Planck temperature and isotropy measurements and extend them now out to L of say 3000, 4000 at very high signal to noise. So we're both extending the temperature power spectrum measurements. And then in polarization, we're actually just basically doing better than Planck on almost all scales. So this is the same type of plot for the E-mode polarization power spectrum, where again, this is the signal to noise per L. So this isn't the CLs themselves, it's the signal to noise on the CLs. But what you can see in this graph is that, the ACT DR6 signal to noise is higher than the Planck signal to noise on all scales that we measure from the ground. There are some subtleties about why we don't have the low L data, which is related to the noise that the atmosphere induces in our maps. But basically, from L of say 500 or so, we have just incredible signal to noise um, on the E-mode power spectrum. So this gives us great statistical constraining power, which now we're using to look for lots of interesting signals in the primary CMB. I'm just going to show you a few forecasted results. We've actually completed a lot of the scientific analysis, but I can't yet show you those results because the papers are not yet on the archive. But stay tuned; they will be out relatively soon. So I'm just going to show you some forecasts here for now. So the rightmost column of this table is the forecast for a combined analysis of the DR6 power spectra plus Planck power spectra. So within lambda CDM, the gains, they're not zero. We improve constraint on H naught, for example. We improve the constraint on the scalar spectral index as well. But it's really beyond lambda CDM models where we start to see significant gains. Really, they come from pushing these measurements out into the smaller scales that Planck does not probe. So, for example, N effective, which I told you about earlier, we're hoping, or our data are precise enough to shrink the error bar by almost a factor of 2 on that parameter. Um, and of course, it'll be interesting to see where it lands. There's lots of other interesting things. For example, running of the scalar spectral index, so the next order deviation of the power spectrum in the slow roll expansion. We should have, I mean, the error bar that we get on this is also the best error bar from the primary CMB to date. Um, so there are some hints of running of the spectral index in Lyman alpha forest data that I think make it interesting to check that, um, as well as a huge array of other beyond lambda CDM models. Let me just tell you in a little bit more detail about one of the new physics models that I was mentioning in the H naught slides a few minutes ago, and then we'll move on. Um, so this model, early dark energy, has received some attention in the literature as being a viable way to increase H naught inferred from the primary CMB. So let me just tell you very briefly how it works, and we can talk about this in more detail also later. The basic idea here is that you introduce some new uh, pseudoscalar field into the Lagrangian of the universe. It's has a potential that's set up in such a way that it's initially frozen on its potential due to Hubble friction. So the equation of motion looks like a damped harmonic oscillator, and the damping term is due to Hubble friction. It just holds it in place on its potential. So this is then sort of like during inflation, it's acting like this field is acting like dark energy. So its equation of state W equals -1. But then eventually the Hubble parameter continues to drop, and when it becomes a order of the field's mass, then the field will start to roll down the potential and oscillate around the minimum. And the equation of state then depends on the shape of the potential that you've constructed. It's very important that you don't want the equation of state at late times to be W greater than zero, or sorry, to be W equals zero or less than zero, because then it will stick around and act like an additional contribution to the energy density at late times, which is going to mess up measurements of the distance redshift relation and other things. So the canonical potential that satisfies these kind of constraints and has been found to fit the data from Planck reasonably well. Has a form that looks like this. So it looks like 1 minus cosine of phi taken to a higher power, n. So the standard axion potential would just be v of phi proportional to 1 minus cosine of phi. But the axion potentials violates this third constraint here. So it would have a late time equation of state W equals zero. So the axion will look like an additional contribution to the dark matter, which is not acceptable from a phenomenological standpoint. So the typical values that have been studied are n equals 2 or n equals 3. And I'll show constraints from previous data with n equals 3 on the next couple slides. So here's a picture that perhaps tells the story a little more in a little more detail. So I'm showing on this graph is the fraction of the cosmic energy budget that's stored in this early dark energy field as a function of redshift. And this is for a model that can have a significant impact on H naught that you measure from the CMB. So the idea is that around redshift of a few thousand, so near matter radiation equality, that this new field contributes roughly 10% of the total cosmic energy budget. And then at this critical redshift here where this value peaks, that's when the field starts to roll down its potential. And you see the oscillations here that are coming from the rolling around the minimum of the potential. So the parameters that we use to describe the model are kind of captured from this plot. So the first parameter we introduce is this FEDE, which is the maximum point reached on this curve, the maximum fraction of the cosmic energy budget stored in this field, and then the critical redshift ZC where that maximum is reached. And then there's one additional parameter that you need to fully specify the model, which is where does the field start on its potentials? What's the initial field displacement? So it's a 3-parameter extension of the lambda CDM model. Good. So then this somewhat busy plot that I'll walk you through has a summary of the existing constraints from previous data and then a forecast for the DR6 data. So this is a posterior plot with these 3 new physics parameters in this model, and then the Hubble parameter. Of course, we're also fitting for all of the usual lambda CDM parameters as well when we do these analyses. So the red, blue, and green are results from real data. So one of the reasons that this model attracted some attention was that in our previous data from ACT, data release 4, there was a mild hint of this new stuff being present. So this top left panel is the constraint on this FEDE parameter. And if you detect the value away from 0, that's telling you that the data are suggesting that this early dark energy was present. So from ACT DR4, the previous data a few years ago, there was a hint of a non-zero value here. That hint was still present if we use just a slice of the Planck data in temperature only on large scales. This kind of fills in missing large scales that we don't see from the ground with ACT. That's the blue result. And again, it seems to hold up some evidence of this EDE. But the full Planck data set, which the results are shown in green for, well, the full Planck data set disfavors the existence of this new EDE field. So the upper limit or the bound that you get from the full Planck TTTEE data pushes this back to 0, and the Hubble parameter back towards the low value from lambda CDM. So this is interesting, but the upper limit from Planck is still, there's still wiggle room here to allow for a non-zero value. So this motivates trying to look for this in the current data in detail, which we've been working on. The orange curves here, finally, are a forecast, like the forecast I showed you a minute ago, for the precision of the current ACT-DR6 data. And here this is combined with WMAP rather than Planck. And this is, in the forecast, I've injected a model that has FEDE of order 10%. So a model that can significantly increase the Hubble parameter from the CMB. And what you can see is that if it was present, like in the forecast, that we would be able to detect this stuff at high significance. So stay tuned. Again, the orange is just a forecast. That's not the real data. But hopefully this is strong motivation that the DR6 data ACT DR6 data have sufficient precision to really make it interesting to go look for these types of new physics signals. So stay tuned. We're in the process of writing up these analyses right now, and you'll see the papers on the archive in the coming months. Good. So are there any questions about this first part of the talk before I proceed to talk about secondary CMB?
I have a question.
Yeah, please.
So I see that when you combine the result of Act DR4 with Planck, you only take Planck until 650. And what happened? And the full Planck data, which I guess is until, I don't know, 1,500 N,
Yeah.
it gives you this standard result. What happens if you would take Planck data to higher L and do the appropriate analysis considering the, the redundancy in data? I
Yeah,
mean,
I think if I follow the question, but yeah, basically, um, if you use the full Planck data set, including out to the higher L's beyond this, then it basically disfavors the existence of early dark energy and pushes you back towards zero on this graph. Um, yeah, so we've done some investigation of the features in the ACT data, well, the old ACT data, the DR4 data, that led to this mild preference. I should have said the preference is sort of at the three-ish sigma level, so it's not a detection, but it's a hint. Um, the features in the ACT DR4 data that seem to be responsible for this are there's sort of a wiggle in the EE spectrum measured from the ACT DR4 data around L of 500 to 700, which we have even in DR4 we had better signal to noise there than what Planck had. So if it's a real thing, then perhaps it's just the case that we were seeing the first signatures of it in the polarization power spectra. Um, but certainly, yeah, the statistical weight of Planck, as of a few years ago, was much better than ACT-DR4. So if you put in the full Planck data set, then it just pushes you back to zero. Even if you tried combining with ACT in the case of the green result here, Planck would still dominate the constraint and push you back towards zero. So I think what's exciting now is that the ACT DR6 data are sufficiently precise that we really can get a completely independent picture of what's going on without having to make use of Planck. Um, so it'll be interesting to see where things land.
and the other question is, what other parameters you vary apart from the ones in the plot?
Yeah, yeah, good question. So we varied the whole usual set of lambda CDM parameters. So matter density, or sorry, cold dark matter density, baryonic matter density, um, the angular acoustics scale, the amplitude of primordial perturbations, the scalar spectral index, and the optical depth, tyrannization tau. So H is actually a derived parameter. So there's a total of 9 cosmological parameters in the fit. And of course, we also have to fit for various nuisance parameters with related to foregrounds and calibration and stuff like that.
And you get the usual values for those, the standard values, or you get some deviation from there?
For the most part, but actually, this is a very interesting point, which is that in the context of this early dark energy model, one of the reasons that it can accommodate a high H naught from the CMB is due to the way that some of the standard lambda CDM parameters shift around when you do the fit. Um, so I wrote some papers on this back in 2020, 2021. So there's some very interesting physics that happen. So one of the things that happens is that while the early dark energy is operational prior to recombination, it's slightly accelerating the expansion of the universe. That then leads to a slight suppression of the growth of perturbations, the same way that dark energy today slightly suppresses growth of perturbations. And that has to be counteracted somehow. And it turns out that what the data prefer is to increase the cold dark matter density from the early universe so as to counteract that suppression. So when you do these fits to the CMB in this EDE scenario, you generically get higher values of the cold dark matter density, which then leads to a prediction for a larger value of the S8 parameter at late times. So generic prediction actually is that you actually slightly increase this so-called S8 tension that I haven't talked about here. Um, Yeah, there have been a number of papers back and forth in the literature about this particular issue and the impact on large-scale structure data. But it's a very important point that the standard lambda CDM parameters do actually move around in these fits. They don't stay exactly the same. Okay, good. So I have some backup slides actually, I think, on some of the ED related physics, so we could talk about that afterwards if you're interested. Okay, in the second chunk of the talk, then let me turn to tell you about some recent work that we've been doing. Looking for different signatures of BSM physics in the secondary CMB. So this is work with a smaller group of people from Columbia and Perimeter and Cambridge. Okay, so let me just briefly explain what I mean by secondary CMB. So the CMB secondary anisotropies are signals imprinted into the CMB due to physics operating as the photons propagate through the universe on the way to our telescope. Um, so there's some famous ones that will have heard about, like gravitational lensing of the CMB, where the path gets bent by the gravity of large-scale structures. Um, there are effects due to the evolution of gravitational potentials, like the ISW effect. And then there's effects related to scattering of the photons off of free electrons. These are variants of the Sunyaev-Zeldovich effects, like the thermal and kinematic SZ effects. So these are all standard things that are already studied. What we're going to talk about here are some possible BSM uh, secondary anisotropy signals. So these are going to be due to conversions that could happen that would convert the CMB photons into other states as they propagate. And these will generically leave what we call a patchy dark screening signature in the CMB. All right, so let me just briefly introduce the particle physics models that we're thinking about here. Um, so there's these four categories of so-called portals that are largely studied in the Pheno world between the standard model and the dark sector. The vector portal, the axion portal, Higgs portal, and the sterile neutrino portal. I'm just going to focus on the first two here because these are the ones that leave the relevant signatures that we're thinking about in the CMB. Um, so the operators that are relevant are written down over here. So the first case, we're thinking about a new vector. So this is just a dark photon, which has its own field strength tensor, F prime mu nu, which mixes with the weak hypercharge in the UV or in the IR. It just looks like a mixing with the usual Faraday field strength tensor, F mu nu. Um, and then secondly, we'll look at the pseudoscalar, the axion portal. And the relevant operator that we're going to care about is this one here, this Chern-Simons coupling, where you have an axion field and then you have a FF dual, where this is the usual field strength tensor of E and M. So I'll tell you about the physics in just a second in more detail, but the basic idea you want to have in mind is that when the plasma mass of the standard model CMB photon becomes equal to the dark photon mass in the first case or the axion mass in the second case, then you can get a resonant conversion that converts the CMB photons into these new states. Um, and the fact that it's resonant is why we can get a very tight constraint here on the coupling parameters in these terms. So if you put in some numbers, which I'll show you in just a minute, you'll find that you're sensitive to masses that are on the order of 10 to the minus 13 to 10 to the minus 11 electron volts. So these are very light uh, dark photons or light axions that we're talking about. So let me start with the dark photon. The Lagrangian looks like this. So the first term we all know and love. And then we introduce a new dark photon that has, again, same type of kinetic term for itself. It's also going to have a mass term shown here. And then the mixing between the standard model photon and the dark photon is this F prime term here, which has a coupling, dimensionless coupling epsilon that we're going to try to constrain. So we're looking for a kinetic mixing between the standard model photon and the dark photon. So what happens that we're thinking about photons propagating through the universe. After reionization, the universe is in a fully ionized state. So when you have a photon propagating through an ionized medium, it acquires an effective mass just due to the Thomson scattering happening. Um, and that effective mass goes like the square root of the number density of free electrons. If you put in some typical values in the intergalactic medium, you'll find that the typical plasma mass that the CMB photon acquires in the late time universe is around 10 to the minus 11 electron volts. So there's a fun calculation you can do then, which is that if that plasma mass becomes equal to the rest mass of the dark photon, then you can get a resonant conversion process that converts between these states. And this is directly analogous to the so-called MSW process for neutrino oscillations in matter, if you've studied that. Um, so the result of the quantum mechanical calculation that you do for the conversion yields this conversion probability shown here, where the important things to note are that it scales like the square of the coupling between the two uh, fields, and then the frequency dependence is going to be important for us. So also the fact that it goes like 1 over omega, where omega is the frequency of the CMB photon. So that's the dark photon case. The axion case is similar but a little bit different. So the relevant term in the Lagrangian is again this Chern-Simons type of term, AFF dual. If you evaluate this, it just looks like electric field dot magnetic field multiplying an axion field. And we're going to look for this to constrain this coupling between the axion and the photon, GA gamma gamma. So what's happening here is a similar thing, but we need now an ambient magnetic field in order to get conversion from the photon into the axion, because this involves three fields, AFF dual. But otherwise, it has a lot of similarities. So again, we're looking for resonant conversion. So we're sensitive again when the plasma mass of the CMB photon is equal to the axion mass in this case. So of the same type of mass range that we're sensitive to. But the quantum mechanical calculation to compute the conversion probability is a little bit different because of the ambient magnetic field. The result is shown here. So the relevant features now are that this scales with the square of the coupling parameter, but also with the square of the magnetic field strength. So we're going to have to know something about the magnetic fields that are present in order to derive a constraint. The other thing I'll highlight is that the frequency dependence now scales linearly with the photon frequency as opposed to inversely, like we saw in the dark photon case. Okay, so here's a sort of cartoon picture of what we're looking for. So CMB is over here on the right, the surface of last scattering. The CMB photons are propagating through the universe. Occasionally, they'll go through a dark matter halo, which has a whole bunch of free electrons in it. And this is shown for an axion case. There's also a magnetic field within the dark matter halo. So there'll be some particular region within the halo where the plasma mass of the CMB photon becomes equal, happens to be equal by coincidence, to the axion mass. So you get a resonant conversion that happens at that particular place. Um, uh, and you'll get one both as it goes into the halo and as it comes out of the halo. And the conversion probability depends on the coupling between the photon and axion and the strength of the magnetic field in the halo. So what we would see if we looked into the sky with Planck, this is exaggerated for emphasis, but what we'd see is at the location of, say, a galaxy cluster or a galaxy, we'd see a cold spot in the CMB coming from the conversion of the CMB photons into the axion, because we don't detect the axion or the dark photon. So this produces a spatially varying spectral distortion in the CMB. And it's tracing the large scale structure because it happens at the location of galaxies and clusters. So if you've studied the thermalized Z effect, for example, it's a very similar type of idea. Okay, good. I think I've said all of these things. So here's a little more detail then about what we're looking for. So the relevant reason or the relevant feature of these scenarios that makes them so nice to constrain with our data is that they have a non-trivial frequency dependence or spectral energy distribution. So this is the for the dark photon, this is what the signature looks like in the CMB as a function of the frequency. So X here is just dimensionless frequency. Um, the term in parentheses is not that interesting. It's just a conversion between specific intensity units and delta T units. But the term before that captures the relevant feature of the spectral distortion. So in the dark photon case, it goes like 1 over frequency, and in the axion case, it scales like the frequency. So these are, of course, different than the black body spectrum of the CMB, which lets us then look for these signals. So this is a graph showing what those SEDs look like. So this is in the usual units that we use for CMB analysis, where the black body spectrum of the CMB has a value of 1 at all frequencies. So that's the black line. Um, so the dark photon case is the magenta curve shown here. So due to this 1 over frequency, it blows up as you go to low frequencies. And the axion is shown in cyan. And because of this scaling with frequency, it increases as you go to high frequencies. The fact that it saturates is due to the use of these delta T over T units. For comparison, some of the other signals in the microwave sky are shown as well. So the thermal Z effect is in dark red. It has a famous zero crossing at 217 gigahertz. And then an important contaminant for us is going to be the cosmic infrared background, which is just dust emission from other galaxies in the universe. And that has a very steeply increasing spectrum with frequency. But the beautiful thing is that all these signals have different frequency dependence. So if you have multi-frequency CMB data, you can try to isolate them and make maps of them. So that's what we did. We have a lot of powerful tools for doing this. In particular, we used this code called PyILC that I wrote a few years ago, and Fiona McCarthy and I used for studying the thermal Z effect with Planck data. So this is a needlet internal linear combination code. Think of it as a big hammer that we can use to basically crush this problem and look for any type of frequency dependent signal that we want in the CMB. This is apparently the largest hammer that anyone has made. There's a person in this picture behind the graph here who's about this tall. So I think PyLC is a big hammer that we can use. So I'm just going to give you a quick introduction to how this type of internal linear combination component separation works. And you can ask me the details if you want to know the math afterwards. So the basic idea is that we have some set of frequency maps, so intensity of the sky at different frequencies. And here you can see the galactic plane, for example, in equatorial coordinates. And we want to find the linear combination of those maps that satisfies the constraint of having minimum variance and also having an unbiased response to the frequency dependent signal that we're looking for. So the classic case is to look for an unbiased response to the CMB blackbody spectrum, and that's doing that analysis produces the Planck map that I showed you at the beginning of the talk. But we could just flip one line in the code and say, let me instead look for a signal with a frequency dependence that looks like this dark photon distortion or like this axion distortion. So that's what we did. There's also a bunch of sort of cool tricks here. We do the analysis on what's called a needlet frame, which is a mathematical space that's sort of a hybrid of pixel space or real space and harmonic space or Fourier space. And we also impose some external constraints on our linear combination that null out contributions from contaminants like the thermal Z effect. So, skipping past lots of details, these are the results of doing the analysis. So let me start with the dark photon case. So the raw maps that we get out if we run the needlet ILC code are these ones over here. This is the southern galactic hemisphere and the northern galactic hemisphere. And when we looked at these, we said, oh, this is interesting. There are some cold and hot spots. What are they? So for example, we see a cold spot location of the Coma cluster, a famous galaxy cluster. It turns out, though, that this is just contamination from other signals. So we impose lots of these deep projection constraints to null out known contaminants, again, like the thermal Z effect. Turns out that this Coma cluster spot was just from the thermal Z effect. And after you impose that constraint, then it goes away. So we do a lot of checks to get the cleanest possible map that we can. And then we're going to cross-correlate these maps of this dark photon distortion with a tracer of large-scale structure to look for a correlation between these fields. Because again, the conversion process should be happening at the location of dark matter halos, which host galaxies and clusters of galaxies. So we use these galaxies from the Unwise sample, which is a very, very large catalog containing hundreds of millions of galaxies. So we looked at both this blue Unwise galaxy catalog and the green one, which are at redshift 0.6 and redshift 1.1. So skimming past lots of hard work to clean out the foregrounds, the final results that we get are the empty circles shown on this plot. So this is another plot that shows the power spectrum as a function of L, but now this is a cross power spectrum between the dark photon distortion map and the galaxy density map. And what you can see is that the empty circles are consistent with zero, so we don't detect a dark photon signal. And these are various theoretical predictions for different values of the dark photon mass and the coupling of 10 to the minus 7. So we don't detect anything in the blue galaxy catalog or in the green galaxy catalog. And from the null detection, we can then convert that into a constraint on the strength of the coupling for various values of the dark photon mass. So here's the final punchline result. Um, these are upper limits now on this uh, connect mixing or coupling parameter as a function of dark photon mass. And you'll see that it's the mass range that I told you about earlier from roughly 10 to the minus 13 to 10 to the minus 11 electron volts. The previous constraints are the light blue region, and our new constraints are in red from the two different galaxy samples combined. And you can see that we're about 10 times more sensitive than the previous analyses in this mass region. Um, so I thought that that was cool. It's the first time anybody has looked at this type of signal in the CMB. So the fact that it's the leading probe over this mass range, I think, is quite interesting. One fun thing about these type of constraints that I want to emphasize is that these don't require the dark photon to be the dark matter. So the only thing we rely on is that this term exists in the Lagrangian. Um, the dark photon doesn't even have to be cosmologically stable necessarily. Let me maybe skip this in the interest of time, but of course we have to know something about the electron uh, density profile of the halos in order to derive these constraints. For the most part, we're not too sensitive, but if you assume a different model for the electron uh, distribution, you get a slightly different constraint. Um, Let me then turn to the axion case. So the conceptual idea is exactly the same as before, except we're just going to look for a different frequency dependent signal in the axion case rather than dark photon case. So these were the first maps that we produced looking for the axion distortion. Um, this is in a different projection of the sky, but southern galactic hemisphere, northern galactic hemisphere. Again, if we don't impose any of these deprojection constraints into the ILC procedure, you do actually see some signals at the location of, for example, the coma cluster, which is up here. So we have to impose these deprojection constraints to kill off the foregrounds, and then we end up with this map over here on the right. We're going to cross correlate again with these unwise galaxies, very similar type of analysis. And skimming through all the details, then here's the final results. So the top panels here are in the case of the unwise blue galaxies for different ways of cleaning out the foregrounds. And you can see that the results are generally very stable and consistent with zero. In the case of the unwise green galaxies, we actually were not able to obtain a sufficiently stable result. We think that this is because there's significant cosmic infrared background emission that comes from these unwise green galaxies, and cleaning out this CIB contamination was too hard for us to get a stable result. So we discarded the green galaxies in the axion case. But in the blue galaxies, we have a nice robust result that's consistent with zero. So we can then convert that into, again, a bound on the coupling between the photon and, in this case, the axion. So here's the results. Well, this is just showing the cross power spectrum in a little more detail with two different theory predictions for different axion masses and a coupling constant of around 10 to the minus 12 inverse GeV. So we can then take the data points, convert them into a limit on the coupling, and this is what we get. So again, this is similar type of mass range as what we looked at for the dark photon, and upper limits now on the axion photon coupling over that mass range. So the tightest laboratory constraint in this mass range comes from CAST. There are other astrophysical constraints which are shown here in gray, and then our new constraint is shown in red. So we don't quite hit the most tight current constraints. But one thing that we do think is nice is that the other astrophysical constraints that are shown here come from studying individual objects like Messier 87 or M82. Um, and so you have to model, for example, the magnetic field in this particular galaxy at very high precision to derive a constraint. Whereas in our case, we're measuring a ensemble average signal coming from tens of millions of galaxies. So we're much less sensitive to the details of the modeling of some individual system. So in that sense, I think they're maybe more robust, but even if you don't think so, they're at least complementary to the other constraints. We don't detect anything and we get a pretty tight upper limit. Just like the dark photon case, these constraints don't require the axion to be the dark matter. It's just that this coupling term just has to exist in the Lagrangian. Good. We also studied the dependence on the assumed electron distribution model and as well as the magnetic field model. I'll skip these in interest of time, but I'll just note that we considered a really broad range of magnetic field models and find that the constraints only change by a factor of a couple. So it's pretty robust to the assumption of how the magnetic field behaves in these galaxies. So let me just then finish this chunk of the talk, and then I'll start to wrap up with a quick overview at the end. So I think these secondary anisotropy signals are really cool. This is the first, these are the first observational analyses of these particular BSM signatures in the CMB. Really just starting to scratch the surface. So for example, the axion case, there are some really cool signals in polarization that we haven't yet started to look into. And then people have thought of very clever signatures that could also exist in the time ordered data stream of a CMB experiment, which we haven't looked at those, for example, with ACT yet. And then I'll also just mention that if you go back to these types of constraint plots, this was for Planck data cross-correlated with unwise. But of course, we have much better CMB data from ACT and Simon's Observatory, as well as bigger galaxy catalogs soon to come from LSST. And other surveys. So these constraints we forecast should improve by a factor of 10 just in the next few years with upcoming data sets. So it should be fun to revisit this in the near future and maybe we'll detect something. But if we don't, we'll continue to push the upper limits down even further. Good. So let me just then wrap up. I think we're probably just about out of time. So I just want to give you a quick overview then of the experimental landscape, where things are at and what's going to happen in the next 5 to 10 years. So Planck, of course, is finished. It's a great experiment. We're still using the data for lots of cool stuff, like I just showed you. With ACT, we observed through August of 2022. That was when the telescope had its final night of observing, and then it suffered a mechanical failure, and we decided to decommission the telescope. With ACT, we observed close to half the sky. I showed you the sky coverage. I've showed you that our noise properties have now surpassed Planck. So we're doing lots of cool cosmological parameter analyses right now. Stay tuned for those papers very soon. Our colleagues at the South Pole also have some great data that should come out, I believe, this year. The next big thing that we're building in northern Chile is called the Simons Observatory. The first of the SO instrumentation, which are these smaller telescopes just meant to look for primordial gravitational waves, those telescopes have started observing as of a few months ago in 2024. The remaining piece of the hardware is this large aperture telescope shown here, and that is in the final process of integration right now and should start observing within the next couple of months. So it's a really exciting time for SO. It will cover also about half the sky. The noise levels improve upon those of ACT by another factor of 3 or so, with similar high resolution and multi-frequency coverage. So it's going to be a really sensational experiment. Then moving on from SO, we actually now have obtained funding from the NSF here in the US for what's called the Advanced SO project, which I'm very heavily involved in. This will fill out the remaining uh, slots in the focal plane of this large aperture telescope with additional detectors, which then reduces the noise levels another factor of about 2 below those of the original SO. And that will then continue observing all the way into the mid 2030s. So it gives us about a decade roughly of really nice data coming from Saratoga. And then looking further ahead, the big project You've probably heard about it. It's called CMBS-4. Um, the original plan for this project was to start observing around 2030. There's been various delays in the US about this. I think it's more like 2034, 2035 now. Um, it would cover an even larger sky fraction and have noise levels that surpass those of advanced SO by another factor of two or so. Um, so we should really be squeezing every drop of information that we can out of the CMB. I haven't talked very much about primordial gravitational waves, but a major part of these projects is also to look for B mode polarization from inflationary gravitational waves, and I can certainly tell you more about that if you're interested. So just to summarize in one plot here, the outlook with the just the E-mode polarization power spectrum, which is going to become the workhorse for looking for new physics in the primary CMB. This is the signal, lambda CDM signal of the E-mode power spectrum in black, and then the noise power spectrum for those different experiments that I just told you about, where the bands here capture the range of uncertainty for advanced SO and then CMBS4. What you can see is that we push the noise further and further down as we build out these more sensitive experiments, um, such that we should map the E-mode polarization to levels comparable to where we're at with temperature um, within the next decade or so. So there's really immense discovery potential to look for very subtle hints of new physics out here in the high resolution CMB. All right, let me then wrap up. I hopefully told you about some interesting things, both new physics in the primary CMB. Please stay tuned for cool results from ACT that are going to come out quite soon. Um, and then also some new avenues for secondary CMB studies of BSM physics, which I think we're only just beginning to explore. So here's a nice, beautiful picture of Saratoga in the Atacama. Uh, Really happy to be doing this great work from northern Chile, and I'm excited about the next 10 to 20 years of what we'll do from there. So thanks a lot, and I'm happy to take questions.
Okay. Thank you, Colin. Anyone have any questions?
Yes, go ahead. Hi. Hello. Thanks for the talk. I have one question about I am a bit confused when with one thing. The existence of the action has proved that with that maps show it in the presentation.
Yeah, these maps, yeah.
Yeah, the the existence of action is proven. Explain.
Oh no, no, sorry. No, it's certainly not proven. Um, yeah, so what we do is what we're looking for really, let me just go back then to here. So what we're doing in that analysis is that we're gonna take the multi-frequency maps from Planck. So basically these type of maps, this is the intensity of the sky at different frequencies. And we're gonna try to synthesize out of those multi-frequency maps a single map that would represent this particular spectral depend. Well, that's the dark photon. Sorry, the axion case. It's this particular spectral dependence, the cyan curve shown here. So you basically apply some weights to your maps and then add them up in such a way that you would get out a map of this axion distortion signal. Um, Once you make that map, it's going to be noise dominated because this is going to be a tiny signal, or else we would have already seen it. So it's a noise dominated map. And moreover, it's going to be sensitive to other foregrounds that could leak into that map because we only have a limited range of frequency coverage. If we had perfect frequency coverage, we could get rid of all the foregrounds and stuff, but we only have a few frequencies. So there's some foregrounds that leak in. So, uh, these maps show different ways of treating the foregrounds that could leak into the map. But what you should really think of are these maps are just noise dominated maps. We looked at the auto power spectrum of these maps to look for a signal. It's consistent just with noise and some residual foregrounds. It turns out that the most sensitive search strategy is to take a map like this and then cross correlate it with a large scale structure uh, tracer like a galaxy map. So these maps contain millions of galaxies, and we're just going to look at the cross correlation function between these data sets. And if there was no, um, well, let's say if there was an axion photon coupling, then what you should see is that there should be a small correlation between um, these maps. Um, of course, what we detect is a zero cross correlation, and so then that gives us an upper limit on an axion photon coupling parameter, which is what this graph then summarizes. So we don't detect axions, certainly not. If we did detect axions, this would be in the news, and you would have heard some exciting uh, big discovery results. So we don't detect them, but we get a nice upper limit from the fact that we don't detect this coupling.
Thanks. Another one question.
Yeah.
I one question. Uh, it is considered. I don't speak very well. What is the role of a new metric in the description of the universe in this study? A description of a new metric is considered inside this studio?
I'm not sure if I fully followed the question. Are you talking about the metric of space-time?
Yeah, because
Oh, okay. The metric actually is not strongly affected. Um, yeah, so the metric here is the usual perturbed flat FRW metric that we also have in Lambda CDM. So these type of signals here are small enough changes to the cosmological history that the metric is largely unchanged compared to the standard model. Yeah, I'm not sure if I fully follow it, but in some of the other stuff I talked about earlier in the talk involving the primary CMB, for example, with this early dark energy model, for example, in a model like that, the evolution of the metric is actually changed um, in a non-negligible fashion, yeah, compared to lambda CDM. So we take that into account. We put those models into an Einstein-Boltzmann code like CAM or class, which simultaneously solves for the evolution of the metric perturbations and the different energy density components.
Point. I wanted to ask you something. Since you're cross-correlating this action with large-scale structure data, is it expected new to see the impact of this action or dark photon in any observable at large scale?
I think for these particular, I'm not sure if I fully follow, but in this particular mass range, the main signal that you could look for is this type of resonant conversion of the CMB. Um, One might wonder about these other types of constraints. The gray bands on this plot are from non-resonant conversion. So if you have a very close by system like a nearby galaxy, um, or something with a very strong magnetic field like a supernova, then you can actually look for non-resonant conversion, and that turns out to be pretty sensitive. For axions of different mass ranges, there's lots of different probes that come into play. People have looked for signals from axions decaying into photons of different energies, for example. Um, yeah, but in our case, you see this. You would see a correlation just from the fact that um, the relevant resonant conversion that would happen is happening within dark matter halos. And so that leads to a correlation between the positions of the dark matter halos, i.e. the galaxies, and the CMB distortion that's induced.
Thank you.
Mhm.
Anyone in the Zoom, maybe? Okay, if not, let's thank Colin again.
Thank you. I hope to make it in person at some point in the next few years. It'd be fun to go to the site also and get a chance to see Chile.
Some of us are trying to have the next SO meeting in Chile, so stay tuned.
Hi,
Sorry,
Brandy.
I joined later because for me it's 8 a.m. right now, so I'll watch your record. But yeah, thanks, Colin.
Yeah, good to hear you.
Okay, thank you. Thank you very much for
Okay. Thanks a lot. Yeah, feel free to send me an email or follow up if you have any questions that you want to discuss.
Thank you.
Thanks.
Bye.